Welcome to section 7.2. I'm going to call this section B. We're working on integrals focused on sine and cosine. So take a look at this. Integrals involving powers of sine and cosine. Notice the format that's happening here. So we're looking for the type of problems where we get sine raised to a value and cosine raised to a power there. So sine of mx and cosine to the power n of x dx, where either m or n is a positive integer. To find the antiderivatives of these forms, try to break them into combinations of trig integrals to which you can apply the power rule. For instance, you can evaluate sine to the fifth power and cosine to the first power with the power rule by letting u be your sine, and then du becomes cosine dx, and we've got that cosine dx, so we can substitute du into that. So when we do this, we will make use of some of these old trig identities, the Pythagorean identity where we get sine squared plus cosine squared equals 1, and keeping in mind that then 1 minus sine squared x equals cosine squared x. That will be of use. And also 1 minus cosine squared x equals sine squared x. Also, taking a sine squared down to a double angle type idea. So 1 minus cosine of 2x divided by 2, or cosine squared x is 1 plus cosine squared, cosine 2x divided by 2. So those half angle identities will be useful for us. These are just guidelines, and they give us different scenarios to consider. If the power of sine is odd and positive, the idea is we're going to save one of our sines to convert and save out and then convert everything else to cosine. If I pull one of these sines away, this will give me an even power of sines and then an odd number of sines here, powers of sine. I can save this for my du sub, and I can convert this into a cosine function using that Pythagorean identity one. If I have a cosine that is odd, then I can save one of the cosine factors, factor it away, so that I'm splitting up my cosines into an even number and an odd number for the powers, and saving that back for the du. If both of them are even, if sine and cosine are even, we will make repeated use of the identities, especially these ones, okay? So those end up, I think, being the harder ones. So let's go through these different examples, and then that will be the homework for the night. So, problem A. What I notice is that I have an odd degree for my sines and an even degree for my cosine. So this would kind of follow that guideline on the front side of our notes, the guideline where we're talking about an odd power of sines. And for that, it suggests that you break this sine down into a sine squared and a sine to the first power. Add the powers and we're back up to a sine cubed. This sine x1 here, I'm going to slide that over. So let me put my cosine squared in between here, and then I'm going to pull that sine x1 off to the end. This is kind of going into reserve for my du sub. What I'm going to do then is I'm going to write sine squared using the Pythagorean identity 1 minus cosine squared x times cosine squared x times sine x dx. And if I go ahead and distribute, I would have cosine squared x minus cosine to the fourth x multiplied by sine x dx. Now, a little du sub, or u du. If I let u equal a cosine, Then the derivative of that would become, the derivative of cosine is negative sine x dx, which then I could place as a negative du is equivalent to a sine x dx. And there's our sine x dx, so that's going to get replaced with negative du. Every place I see cosine, I'm going to replace it with u, and then where I see sine x dx, it's going to get replaced with negative du. So this will give us the integral. Cosine squared will be a u squared. Cosine to the fourth will be a u to the fourth. Sine x dx is getting replaced with negative du. I'm going to put my negative sign out front. And now, look how cool this is. We are left with something that's not all that difficult to integrate. U to the third divided by 3 minus u to the fifth divided by 5 plus c. Subbing back in and distributing my negative, u was set up to be cosine, so that'll be cosine to the third x divided by 3. Negative times negative gives us a positive, and I'll have a cosine to the fifth x divided by 5 plus c. And we have our integral back to an original function. Let's just call it y. Y equals. Pause that, walk back through the steps if you need to. I'm going to hit clear and move on to part B. Question B says, let's work with a cosine cubed of x over 3. So cosine cubed is an odd power of cosines. This, look under guideline number 2 on that previous screen. Guideline number 2 says go ahead and split off the cosines so that we get an even number of cosine power, so cosine squared x, and branch off one of the cosines and put that kind of in reserve for our du substitution. That means that I need, if I'm going to use this be my du, then that came from a sine function being my u. This can convert into sine very easily, so we can take that cosine squared, rewrite it as 1 minus sine squared x, and then I'd have my cosine x dx. Off of this, I'm going to branch over and do my u sub. Let's let u be sine x. Then du will be cosine x dx. And that's precisely what I have. That's a complete match, so that's going to get replaced with du. Okay, back over to the integral work. The integral will equal 1 minus u squared, because sine was set up as our u sub. Cosine x dx is the same thing as a du, so replace it with du. Now integrate. Whoops, what's this equal sign doing here? We could say some function y is equal to, or y equals. Now, integrating this. The integral of 1 with respect to du will be a u minus u squared will become a u cubed divided by 3 plus a c. Now let's substitute back in for u. U originally started out as a sine. So this will be sine x minus sine x divided by, cubed, divided by 3 plus c, because that was u cubed. And that one is done. This idea of an odd power being able to be branched apart into an even and an odd, and that sets us up really nicely for substitution method. So clear? And now let's finish with this last one. No, the c didn't come with it. There we go. So we've got c and a definite integral this time. All right. So I notice that I have even power and an even power. And for that, we do some fancy substitutions. Let's utilize 2 of those trig identities. Sine squared x could be rewritten as a 1/2 of 1 minus cosine of 2x. And then cosine squared x, if you look back to the screen before this, this is its trig identity. Those two are equivalent. Those will be handy because we're going to be able to get rid of this squaring, which is making it difficult to integrate. But I can get it over in here where I do not have any more powers. The power is 1. And cosine of 2x, that's not too bad to deal with when we're integrating. So this integral, I'm going to deal with the definite part of that later. So right now, I'm just going to focus on getting this integrated. Sine squared x can be replaced with a 1/2 1 minus cosine 2x. Cosine squared can be replaced with a 1/2 1 plus cosine 2x dx. If I take my 1/2 times my 1/2, I end up with a 1/4. So let's pull that forward in front of the integral. And that leaves me with a 1 minus cosine 2x and a 1 plus cosine 2x dx. 1/4 the integral of 1 minus. If I FOIL this, when we multiply it by each other, I'm going to get 1 minus, the middle terms will disappear, and I'll have a minus cosine squared 2x dx. I still don't have anything I can really set up with a u sub. If I let u be cosine of 2x, that's going to lead me to a du of 2, derivative of cosine would be negative sine 2x, and then chain rule derivative 2x produce that 2 for me. But I don't have any signs present, so that's kind of troublesome. So this is not equipped yet to be a u sub. But what I can do is repeated use of these identities. So let's transform this squaring into another half angle identity. So 1/2 cosine of what? Oops, this is not quite right. Sorry about that. 1/2 of 1 plus cosine of something there, and then I'll have my dx. Okay, so the pattern, let's go back up to the original identity here. When I have x, I kind of take this value, and when it comes over here, it becomes twice that value x. So keeping that in mind, I'm going to take this original argument 2x, and I'm going to double it, and it becomes then 2 times 2x, so 4x. And now I've been able to get past that squaring. Okay, now this just needs to get cleaned up because I have half times all this stuff. So I'm going to run through and distribute that 1/2. It's really a negative 1/2. So negative 1/2, that's that multiplication, and then multiply it by that, and that's going to be a negative 1/2 cosine 4x dx. But 1 minus a half, that's easy, that's a half. So next line is going to say 1/4 the integral of 1/2 minus 1/2 cosine 4x dx. And you know what, I'm seeing these as being a common factor. Let's pull that 1/2 out front, and that's going to make 1/2 times 1/4, producing 1/8. Okay, so I have 1/8 the integral of 1 minus, remember these halves came out, so I'm at 1 minus cosine 4x dx. Now, this is something I can handle. I am going to integrate this. The integral of 1 will be x minus, you may want to go do a u sub on that. If you have to, go ahead, but let u be your 4x. I'll just do it. du is equal to a 4 dx, therefore dx is equivalent to a 1/4 du. We need that 1/4 as our correcting factor, so this is going to be 1/4. The antiderivative of cosine is sine, and then it would be of 4x because of u, and then plus c. And that's going to look like, let's distribute the 1/8. 1/8 x minus 1/32 of sine of 4x. The plus c we really don't need, because if I bring those intervals back in, and the reason I paused to hold off on those was to see if I needed to do any u subbing, and I never did, so it became x's all the way through, so it's 0 to 2 pi. Those would still be valid intervals for which we are doing the evaluation of. So now we can just put in our values. So I'd have 1/8 times pi over 2 minus 1/32 of sine of 4 pi over 2 minus, do not assume that this 0 is going to zero out. In this first case it will. This was the f of b, and now here's my f of a idea. 0 going in is going to give me 0 minus 1/32 of sine of 4 times 0, which would be sine 0. And indeed, this will zero out, won't it? Here I get pi over 16 minus 1/32. This is like a 2 pi, is it not? And 2 pi, sine of 2 pi is 0, so this becomes 0 minus 0 plus, because minus minus gives us plus. 1/32, sine of 0 is 0, so this is 0, that's a 0, that's a 0. It appears like we get a very nice, concise answer of pi over 16. Homework will be these problems 5, 6, 9, 11, 14, 15, 79, and 80. So none of this, and the others are showing there. So good enough. Thank you.